Thanks, Vanessa. And I'm really sorry this is not happening in Barcelona as it was supposed to be, but like it is what it is. So let's not spend time on that one. So
Next
yeah,
time.
this next time, yes. So this talk is indeed about Mir-BFT, and basically let me start the talk. Okay, so basically, this talk is about consensus. In particular, it's about BFT consensus. And here we use consensus to establish in a blockchain network total order of transactions, right? So blockchain is basically, so sorry, just a second, I have an interruption at home. I'm very sorry. But in the essence of all blockchains is this totally ordered data structure that orders transactions. The transactions can be grouped in blocks, and then blocks are linked to one another, essentially. And then we talk about the blockchain. So the consensus protocol is the one that keeps these replicas of a blockchain at different nodes basically the same. Of course, one of the first blockchain consensus protocol is the Bitcoin consensus, right, based on proof of work. And we are aware of basically problems that come with a nice concept of proof of work. Essentially, this is low performance and high energy consumption. And where the industry is going and where the research is going in the last several years is towards so-called, in the permissionless settings, towards proof of stake consensus protocols, or in permission blockchains for classical BFT consensus protocols where we don't have this essentially issue with proof of work. So essentially, we can get higher throughput, higher performance with less basically energy consumption with different guarantees. So we need to change the assumptions and the model under which the consensus protocol operates. So it's not as nice as and appealing as Bitcoins, but because of throughput and energy, we are essentially moving there. And there are many protocols that attempt basically to be scalable and to have high performance in this domain. And Mir-BFT belongs to this class of protocols, right? So it belongs to the same line of research PBFT, Tendermint, BFT Smart, Algorand, Hotstuff, Honeybadger, and others belongs to. So Mir-BFT is essentially, this is like this work on one slide. It's a robust BFT total order consensus protocol with highest throughput on wide area networks measured with up to 100 and probably more nodes. We didn't measure in details and compare in details, but it probably scales a bit more. As such, it's suitable for permissioned blockchains such as Hyperledger Fabric, but also for proof of stake permissionless blockchains. So I invite you to stay with me regardless of whether you're interested only in permission blockchains or in permissionless blockchains, because the thing is relevant for both. What I mean by robustness, this is probably the only thing that's not crystal clear here, is that the consensus performance should be maintained despite attacks, right? So this is what it means in principle, right? And Mir-BFT is one such protocol. Let me define the problem statement a bit more closely, right? So we are talking about the classical BFT model, so eventually synchronous network. Some call it asynchronous, but essentially we are not, unlike some randomized protocols, we are not in the asynchronous model, but in the eventually synchronous model. And we are talking about optimally resilient protocols. So Mir-BFT actually, to tolerate F Byzantine faulty nodes, which deviate from the protocol, it requires only 3F+1 nodes. Of course, you can throw in more nodes if you want. Any number of clients can be Byzantine. So we assume a client-server model in a sense in which clients submit transactions to a bunch of servers, bunch of replicas, and these are totally ordering the transactions coming from the clients, and basically they deliver the total order. So we are assuming a classical definition of total order. Here I define it a bit informally, so it fits in one line each, right? So agreement, all correct nodes deliver the same transactions in the same order. Validity, nodes, basically replicas of the system, deliver only transactions proposed by some client. Transactions are not duplicated, so we're not supposed to take one transaction of a single client and then deliver it a billion times and call this total order, right? So we don't want duplication. And essentially, we want some property of liveness. So if a correct client submits the transaction to the system, so total order broadcasts the transaction, this transaction should be delivered, or actually must be delivered by all correct nodes. So this is the classical definition. So to understand how Mir-BFT works, I would like just to spend 2 minutes on basically a bit of didactic part of this talk, and to understand bottlenecks of leader-based protocols. So in principle, BFT protocols have traditionally been leader-based. There are several protocols that depart from this, but if you go to textbooks by now, if you go to Christian's textbook, this is what you would see there, right? You would see a leader-based protocol. So in a leader-based protocol such as PBFT, the leader or the primary, who is basically re-elected from time to time, right, according to certain constraints, its job is to assemble this batch or a block of transactions, right? So what the primary does is it assembles it gets the transactions from clients, and it basically assembles them in this batch. And then it goes to this first message in a 3-phase message pattern that follows Braha broadcast, Braha reliable broadcast essentially, and basically sends this to all nodes. So here I have the example of 4 nodes. Essentially, we are tolerating one Byzantine fault, and this is how the protocol would start in the colon keys. Then we have nodes engaging in all-to-all. So this is in PBFT protocol. There are different variants, right? If you talk about Hotstuff, we would have a different pattern here, but just bear with me. This is how it goes in PBFT, right? So there is some ON square communication, so all-to-all communication among nodes, and another one. So for me to explain why we need the second one, it's fairly easy because the primary can be malicious. It can send different batches to different nodes. But then again, to explain why we need the third round, we probably need more time. So just trust me that the primary needs to do it, at least with 3f+1 nodes. If you increase the number of nodes, it actually doesn't. If a node gets a quorum, like a qualified quorum, and here we are talking about a quorum of 2/3 majority quorum of nodes, they're like confirming that it's actually this particular batch that primary tries to order, then at this point it is added to the total order. If there are some inconsistencies due to malicious primary or due to essentially disruptions in the network, then we have so-called view change and the primary is changed. So the question here is, what is the bottleneck in this pattern, right? So it's easy to guess that it's n-square communication that's actually a bottleneck. In principle, it isn't, right? So it isn't because the n-square communication looks expensive, but it's actually not. And the reason why is that basically this second and third prepare and commit messages are basically exchanging just the hash of the batch. So essentially you have it's a very small message and it's load balanced across all nodes, right? So essentially all nodes for second and third message, every node for second and third message sends like n times this very small message, which leaves us, as in particular on wide area networks, the bottleneck of the first message. So it's the primary disseminating all the transactions to all nodes. And that's actually the bottleneck. So what happens is that essentially I have here like just a simple calculation. As n grows, the number of nodes grows, the size of this leader message, not just the message size, but like a cumulative size of all prepared messages that the leader needs to send, grows linearly, which implies that that the single leader BFT theoretical throughput of a protocol such as PBFT basically decays inversely proportional to the number of nodes. And this is what many essential experiments show. And this is because of the first message. It has basically nothing more or less to do with second and third all-to-all communication messages. So this is the first insight, right? And now what we do in Mir, I will just try to capture the basic idea. So in PBFT, PBFT has this concept of watermarks. So it can actually go and propose messages out of order inside the window. So here I have the node 0 being the primary and essentially proposing batch number 0, batch number 4, batch number 8, batch number 12. Right? So the leader can do this in parallel. And of course, we still didn't solve the leader bottleneck. So what Mir does is essentially it shards batch sequence number across all leaders, and in limit, all nodes are leaders in Mir, and they essentially act as leaders in parallel. Which means that, for example, in this example, I have 4 leaders, And the sequence numbers are essentially sharded across all nodes, such as like in modular arithmetic. So node 0 proposes all batches which are 0 modulo 4, right? Node 1 proposes all batches which have sequence number 1 modulo 4, etc. And the same for nodes 2 and 3. And this is the main concept, right? So this is fairly simple. So instead of a single leader in PBFT, we just give an opportunity to multiple nodes to propose messages. So what's the main challenge here? I mean, it's a fairly simple idea. So why don't we have protocols that actually did this before, right? Actually, we have some ideas of multiple leaders protocol, but none of them actually solves the issue that I'm showing on this slide, right? And this is where the novelty of Mir comes in, because Mir solves this issue that I'm going to show. As you allow multiple nodes to propose basically batches in parallel, this is what can happen. So client can be submitting its transaction to many nodes, right? And you can basically forget about restricting the client to submit a transaction to a single node, because the single node can be malicious. And because we want to ensure liveness, we need to allow the client to submit its transaction to more nodes. So it's easy to see that the client needs to submit to at least f+1 nodes in order to satisfy liveness, right? So we need to allow client to submit transaction to more nodes. And as soon as we do that, if, for example, here node 0 and node 1 include the gray transactions in the block, basically because they do not coordinate with each other, and this agreement, basically I just show the first message and there is the second and third. Basically what will happen is this transaction will appear twice. And you can imagine that by basically allowing the client to submit to any node, any transaction can appear in the basically blockchain 3f+1 times. And this destroys the throughput, right? So unless you're solving request duplication, the fact that you're allowing multiple leaders to propose is just not sufficient. And this is what Mir-BFT does. So it's a total order broadcast protocol orchestrating around the following main principles. So it does have multiple leaders, which are allowed to propose a request in parallel. And as we discussed, it shards blocks or batch sequence numbers across readers. Basically, we have multiplexing of several single leader instances into a single total order broadcast, total order. What should be noted here is that there is no sharding, right? So we do shard batch sequence number, but then we multiplex them in a single total order. So essentially, Mir is not belonging to the family of sharding protocols. It's delivering a single total order. It prevents request duplication by a mechanisms that basically is the key contribution of the paper that I will focus on in a bit more details. And it's incrementally built on PBFT, or actually aardvark hardening or PBFT. Aardvark is the NSDI 2009 paper that basically delivers reasonable throughput despite attacks on PBFT, right? But essentially, you can, in the first order approximation, you can think it's built on PBFT. And it's built on several optimizations and implementation particularities that I will highlight as we go. So what's most important feature in Mir is this prevention of request duplication. So let's see how this is done. The main principle is that Mir leaders partition the hash space of transactions into buckets, so-called buckets, using a cryptographic hash function. So it needs to be cryptographic hash function for several reasons. We can discuss them. And which means that, so it just takes SHA-256. It satisfies basically what we need here. And each transaction, basically, if you take the SHA-256 hash, maps each transaction to a unique bucket. Each leader has a different active bucket, and it's allowed to propose in a certain period of time only from this active bucket, actually set of active buckets. And periodically, we do what we call bucket reassignment or bucket rotation. So let's see how this looks at the example. So here I have 4 nodes. I have just 4 buckets. So this is basically the division of the hash space into basically 3 quarters. And each of these parts of the hash space or buckets is assigned to a single leader. So we see that the node 0 is assigned essentially the blue part of the hash space, node 1 the red part, node 2 gray part, and node 3 the turquoise part. In solid lines, we depict active buckets, and in dotted lines, we depict inactive buckets. So as 2 client requests, here I have the client request number 12, it basically hashes to the blue part of the hash space. And for example, request number 13, it hashes to the gray part of the hash space. This means at this point in time, only node 0 can propose transaction number 12, and only node number 2 can propose transaction number 13. And then we go, right? So by this division of buckets, we cannot have request duplication, but we still need to solve the problem, like what happens if one of the leaders is malicious. And here, for example, what happens if node 2 crashes or is simply malicious and censors request number 13. So for this reason, we periodically go to the third bullet here, which is bucket reassignment or rotation. And periodically we say, okay, now it's not node 2 that is responsible for the gray bucket anymore. It's node 3 that is responsible for the gray bucket. And eventually, basically node 3 will propose request 13, even if the node 2 is faulty or it's Byzantine and censors the request. So this is the main principle. Now the leader set. So far I talked about the leader set being a set of basically all nodes are leaders. And this is the default configuration of Mir. It works very well. It works amazingly well with up to 100 nodes as we tested it. So you will see the performance numbers. But you can say, okay, I mean, this looks fragile. So what happens if some nodes fail, right? So what happens with the leader set when nodes fail? Essentially, the Mir, as we implemented, is based on BFT, right? So it still has a primary, but primary in BFT is a lone leader. Now it's not a lone leader. It's supposed to announce its basically fellow leaders. And primary of each epoch, which corresponds to a view in BFT, reliably broadcasts its leader set announcing basically who should belong there. And this is subject to constraints. So primary cannot just broadcast any leader set, right? So we are going towards what we call stable epoch, where essentially number of leaders is equal to the number of nodes, right? In this case, we are not changing the primary, we are not changing the epoch, but we are just periodically rotating and reshuffling the assignment of buckets. So in this case, the epoch has, just like view in BFT, unlimited duration. So there is no limited duration of this epoch, right? However, in recovery epoch, when the number of leaders is smaller than n, then we have a departure from BFT by limiting. Basically, there is a configuration parameter which says this epoch should run only for this many blocks or batches. And then we try to basically, if we successfully finish this so-called recovery epoch, we would try to grow our leader set. If the recovery epoch doesn't finish well, it's basically we experience some faults, then we are going to reduce the leader set a bit more. And you can define different policies there, like how do you grow and reduce leader set, but we implemented very simple policy. If things are good, for example, we are in recovery epoch, the next leader cannot reduce the number of leaders, and it's allowed to grow the leader set if the primary perceives by basically talking recently to other nodes, if it perceives more nodes as alive. And then it's allowed to grow the leader set. If we experience faults or partitions, then the leader sets must reduce. So this is the basic policy that we evaluated, and it works fairly well. As this, you will see that basically Mir, by leveraging several leaders, essentially removes network bottleneck even on wide area network. So for this reason, we have one optimization to Mir, which was previously used by some other blockchain protocols such as Red Belly, which is called signature verification sharding. So we, of course, authenticate all clients' requests. So when the transaction comes in from the client, it's actually digitally signed by client. And the signatures is verified by all nodes in the system. So this is too much, right? Especially when you have all nodes acting as leaders. So all nodes are correct. So in this case, you actually need only F+1 nodes to verify the signature. So, and this is what we actually do. And we say for each and every transaction, we are going to limit, so with signature verification sharding optimization, we are going to limit the number of nodes that actually go and verify client signatures to only F+1. So F+1 to 3F+1 in case F equals 1 is only 1/2, but normally it should be closer to 1/3. In this example, it's actually 1/2. So we are reducing the number of nodes who verify, for example, the signature from this client on transaction 1 to only 2 nodes and not 4 nodes. So this actually helps with the CPU bottleneck that you're exposing when you're removing the network bottleneck by having multiple leaders. Right? And this optimization we use, and I will show you what are the impacts of this. So this is the performance evaluation setup. So we did many experiments with Mir. Baselines are PBFT artwork built on Mir code base for fair comparison. So basically, as Mir is strict generalization of PBFT, it has virtually no changes in the BFT safety part. It only has changes to PBFT for electing more leaders than one. We still have, for example, primary. So primary is announcing its leader set. So we have changes there, right? Then it looks really fair to compare to single leader protocols to PBFT and hardware. For very high throughput, we compare to chain. Actually, a best case fault-free only optimistic chain BFT replication from the next 700 BFT protocol papers that appeared in Transactional Computer Systems in 2015. So this protocol is known to be the throughput optimal protocol, BFT protocol, when there are no faults on local area networks, right? And we evaluate it on wide area networks to see just how Mir performs with respect to very basically optimistic protocol. We also compare it to Honey Badger and Libra. Hotstuff you're using, so for PBFT and chain, we use our code, and for Honey Badger and Hotstuff, we use actual code of these protocols. So we focused on one evaluation. We have up to 16 data centers across the world. When we have more than 16 nodes, we actually co-locate them in the same data centers. These are the specifications of the machine. And we restricted ourselves to 1 gigabit networks, up to 100 nodes. So if we have more, sometimes we have more than 1 gigabit, then we basically throttle the bandwidth to actually limit it to 1 gigabit. And we experimented with 2 transaction sizes. So one is 500 byte transaction size corresponding more or less to Bitcoin average transaction size, and 3.5 kilobyte transaction size corresponding to Hyperledger Fabric, which is more in the paper. Here I'm focusing more on Bitcoin sizes. And we have some LAN experiments. So how does WAN scalability look like? And the numbers are here, right? So red line is your PBFT single leader, basically scalability, as expected. So this is what we discussed. It scales inversely proportional to the number of leaders. Chain is black line. So it scales very well, but remember, this is a very optimistic protocol, right? And then your Mir is, well, the blue line is without the signature verification sharding optimization. So it's like scalability is okay, but the performance is better than any other comparable protocol. So we are reaching essentially without signature verification sharding optimization over 30,000 Bitcoin sized transactions per second on, so basically all nodes verifying the digital signatures of each and every client. And if we introduce signature verification sharding, this is like 60,000 transactions per second with 100 nodes. And this is the top line here. Honey Badger is this line, which is the light blue line here below. So I said we are going to compare to Hotstuff as well, but I removed Hotstuff to a separate plot that I'm going to show you now because of specific, basically setup of the implementation of Hotstuff. And the comparison to Hotstuff is here. Hotstuff code, basically instead of PBFT ON square communication pattern, Hotstuff has ON communication pattern in the common case. But basically, as you see, this doesn't impact scalability too much. There is a certain bump in which Hotstuff performs better than Mir. This is largely due to the implementations of the protocol, but this is basically up to the saturation point of the leader bandwidth, which for us is at 60 nodes, right? At 60 nodes, still, because the Hotstuff is configured to order only hashes and not the full transaction sizes, which are gossiped around. There are issues with this approach. If you do this, you need to make sure that that essentially all nodes get both hashes and the transaction payload. But let's assume you can do it. I mean, this is not something I would recommend, but to order only hashes and gossip the transaction payload without actually taking proper care of it. But let's assume this works. So if this works, Hotstuff throughput grows until a certain point where the leader who essentially sends the batches of hashes only, its bandwidth saturates, and from that point on, it scales inversely proportional to the number of nodes. Whereas Mir essentially scales much better. So in 100 nodes, we have 10x difference between Hotstuff and Mir. And since Hotstuff code doesn't verify client signatures, so this is without client authentication, we configured Mir as well just to have an apples-to-apples comparison. So this is why this plot is a bit stranger than the others, but I mean the takeaway is essentially the same. So Mir scales much better than Hotstuff. What's the impact of duplication prevention? And so here you have the essentially performance of Mir without signature verification sharding. We said this essentially goes up to 30,000 transactions per second with 100 nodes. This is the blue line. And then we allow the client to submit, well, we allow in Mir as well, but client submits to F+1 or 3 F+1 nodes, but then we switched off buckets and duplication prevention in Mir. And basically, you will get the same throughput nominally, but because transactions are duplicated, your good put is essentially what I'm showing here. And the impact of duplicates is severe on the performance. So at 100 nodes, we are talking both submitting basically to F+1 or 3 F+1 nodes having performance of less than 1,000 transactions per second. So this is where the robustness of Mir request duplication elimination really comes to shine, right? So if you have a multi-leader protocol that doesn't care about duplicates, it's going to perform like gray and blue and black line, not like a blue line, right? So this is a key problem. Latency, I didn't talk much about latency, but here it is, right? So PBFT, we have a latency throughput plots, classical ones here, end of chain. So you see that this is with 16 nodes. I took the data point of 16 nodes, so 16 data centers spread across the world. You see that PBFT latency is a bit below 1 second. And Mir latency is a bit higher. It's like 1.5 seconds, but it's still very much acceptable, right? So you can say we have 2x here, but it's the same order of magnitude. So Mir classical latencies, right? And we typically measure latencies when the system is not in the saturation. This is the normal operation point. Basically are between 1 and 2 seconds. For 60 nodes, they're slightly higher for 100 nodes, but still in the order of seconds. We have a bit more experiments which stress robustness. So basically what happens if you have a straggler leader that basically doesn't fail, but tries to slow down the system. And actually Mir performs extremely well here. And some of the experiments are in the paper, which we need to update because we actually did more experiments more on the robustness side and it performs really nicely. But in principle, this ends my talk. I mean, so with this concept, so with multiple leaders and request duplication elimination, we have been able with Mir-BFT to come up with the most scalable protocol up to 100 nodes so far. And that has robust performance despite attacks, despite clients submitting same transactions many times, or despite straggler nodes, etc. Right? So the next steps are essentially we are working with IBM development to have Mir-BFT. We have POC, of course, as a production-ready BFT library that we plan to use in different blockchain projects out there. So this concludes my talk, and if you have questions, I will be happy to answer.